Okay, yeah, please have seats. Yeah, we're a little bit behind schedule, but let's start. So Sergei will give us the second lecture now.
Thank you. I realize that I'm also somewhat behind what I thought will be my schedule, but I hope to get to the experimental part today, but we'll see. But I realize it was a long day, so let me start with a very brief, short summary of what we said last time. So the main points were that first, long string from effective field theory perspective can be thought of as a somewhat unusual system of of 2D Goldstone bosons with well-defined S matrix, which is governed by a non-linearized target space Poincare symmetry, and at tree level, the scattering is just controlled by Nambu-Goto action, and one finds that the theory is integrable, which, well, more specifically, that there is no particle production, and then one loop. There is universal particle production if the number of space-time dimensions where the string is embedded is not equal to 3 on 26. And finally, that's where we stopped. We played a little bit with current algebra of Poincare symmetry, and we found that the conservation of the shift current implies that amplitudes are soft. They vanish when the momentum of one of the particles goes to 0, but that was obvious to start with from the form of the action, but conservation of the boost current led us to this word identity that for arbitrary in and out state with additional Goldstone particle, one gets a relation of this kind, I minus in, where this k is their nonlinear part of the boost current. So it starts ki alpha beta. It starts like xi t alpha beta, where this is a energy momentum tensor of 3 d-2 bosons that comes from Nambu-Goto, and plus there are higher order corrections here. Yeah, that's p plus, right? So that kind of here, I assumed that this p is left moving, so it's p plus, right? Thank you. Well, that this momentum, this on-shell momentum has non-trivial p plus component, right? And 0 p minus. And there is analogous relation for p minus. Yeah, this is just this p which appears here, this on-shell p. Okay, that was the standard technology, how one works with spines. One gets this word identity. And then there was a puzzle, and that's where we stopped. The puzzle was that, well, I didn't show you formulas, but it's straightforward to check that if one confronts this prediction with one loop amplitudes which were derived explicitly, that actually those one loop amplitudes which lead to particle production, they don't satisfy this word identity. So something went wrong. And let me tell you what went wrong. In high dimensions, the argument would work. and for Brannans in high dimensions, indeed, the scatterings are double soft. And so this equality still works in 2 dimensions as well. But the problem is that in 2 dimensions, there are, so in this piece, which usually we assume it to be smooth, actually there are additional singularities here, and that's kind of the price to pay for working with Goldstone bosons in 2 dimensions. And it is diagrammatically, it's straightforward to trace the origin of the singularities. So I'll show them to you now. Well, it's mostly kind of to resolve this puzzle. So we'll see that logic is correct, which is good because kind of one can be a bit worried about working with Goldstone bosons in 2 dimensions. But as I promised, actually this exercise will provide additional bonus for us. Then we'll using this knowledge, we'll be able actually to derive. So far there is a room to have integrable models in d equals 3 and d equals 26. And understanding this issue will allow us to fix the corresponding S matrices. So it's not just a complete waste of time what we're doing here. So the singularities appear in two places. So there are just 2 classes of diagrams where additional singularities show up. It's well, kind of by staring at diagrams, one may convince oneself that that's the case. One is the following kinematics. So this blob here, that's corresponds to that's the insertion of this nonlinear operator. And it's really only cubic part of this operator which will matter, which is in the cubic part, that's the one which I wrote here, which fixed by the Nambogot, and cubic and the laws in derivatives. And so so there is this wavy lines kind of that shows that there is incoming momentum here, and we want to take the limit p plus is going to 0. And there are these kinds of diagrams where I attach this operator and there is some larger large amplitude. And if both of these momenta are, well, I think that would be right moving and this is left moving. Well, if both these momenta have only non-vanishing minus components, then in the limit when p plus goes to 0, this propagator automatically goes on shell. So in higher dimensions, that would be only for very special kinematics when these guys are collinear, but in 2 dimensions, 2 left movers are always collinear. And so this singularity occurs in a generic kinematic. So that's one source of singularities on the right-hand side. One source where this violation of double softness comes about. And there is another source which is similar but somewhat more subtle. Namely, there is also diagrams of this form. So again, it's insertion of the same cubic vertex, same cubic operator. And here I have p minus plus q minus. And when there is a loop like that, which attaches kind of this vertex to larger amplitude. So naively, here one doesn't expect any poles because we're used to associate poles with three-level singularities that loops normally don't produce poles. But what happens? So here the story is again. So when p plus goes to 0, this is there is an on-shell diagram which one can draw where both of these particles are collinear and on-shell. And it's a well-known story in 2-dimensional models that in 2 dimensions sometimes you get poles where normally you expect to have just cuts. So that's, I think there is a Coleman-Thorne paper which studied the appearance of kind of anomalous poles in the Sine-Gordon S matrix, which have this origin. So there are this, and kind of then by just thinking of diagrammatically, it's easy to get convinced. Basically in all more complicated diagrams, in all other topology, there will be some kind of, here it's important that both of these guys, so there are two minuses here, so both of these guys can be left moving, and so there is no kind of, that's what allowed me to put this diagram, to draw on shell diagram here. So they propagate together. So it's rather straightforward to get convinced that that's the only source of these anomalous singularities. But so the bottom line, the resolution of this little puzzle is that, well, in 2 dimensions, there are the amplitudes associated with massless particles. Well, I told you that S matrix here, it's there are no infrared singularities, but here we're not just talking about S matrix. The thing which appears on the right-hand side is this operator. In particular, there is X, which sits without a derivative here. So it's a little bit more subtle object. And there are additional singularities which appear, which violate this naive double softness condition. But there is nothing wrong about that. It's just kind of consequence of what identities is more subtle in this case than one would expect. So that resolves this puzzle, but let's see now the bonus which we can get from this. Namely, so let's ask natural question. So we're left with this possibility that at d equals 3 and d equals 26, the theory may be integrable. Can we determine the corresponding S matrix? And the argument goes as follows. So for a theory to be integrable, in particular, there should be no, so we see that in general, the amplitudes contain part which is non-double soft. And of course, for there to be no particle production, in particular, it's necessary that there is no non-double soft amplitudes which lead to particle production. So let's look at those, and let's look at the 6 particle amplitude. And actually, that's kind of, in principle, the diagrams here, which I can draw here, they can be arbitrary. But let's restrict to inspecting the 6 particle amplitude and the non-double soft. So according to this word identity, the non-double soft. So if I interested in the 6 particle amplitude, the non-double soft part of this other amplitude will be given by the sum of these 2 diagrams. And here the singular part, which leads rise to non-double soft part, is corresponds. So because these guys go on shell and at the singularity, these internal lines. So this M6 is here is also the on shell matrix element, and this M4 here also that's on shell matrix element. So by requiring that non-double soft part of 6 particle amplitude vanishes, one get relation, which I write down momentarily, which which sums together. Essentially, there are actually 3 diagrams here, some permutation of the momentum which one may take, and 1 diagram from there, the only which can give rise to singularity, which involves the 4 particle amplitude and 6 particle amplitude. But now for a theory to be integrable, we know that 6 particle amplitude should be a square of 4 particle amplitude. So this imposing that the non-double soft part of the S matrix doesn't lead to particle production gives rise to the equation just on the 4 particle amplitude on its own, which let me write it here. This way, minus 4 minus and that's contribution from those 3 diagrams and the contribution from that Coleman-Thorne singularity imposing factorization takes this form. So one gets this equation, and well, this equation can be, well, if one recalls the relation of the two particle amplitude, or four particle amplitude, in terms of the phase shift, that's -1, that this equation reduces, essentially, one plugs it back, one gets, well, let me write it. It's e to the 2I delta of 4 plus minus plus minus should be equal to the product to the delta plus minus e to the y delta for k plus k minus. So essentially, well, it tells us that the phase shift should be linear in individual momenta, and this is fixed. Yes. No, I'm asking the question, is it possible to have integrable model? And for the theory to be integrable, in particular, the non-double soft part of the 2 to 4 amplitudes should vanish. And I'm now looking at the non-double soft part of those amplitudes. And those amplitudes, that non-double soft part, which naively shouldn't have been there at all, can be fixed by using these word identities. And so I'm imposing much weaker constraint so far. So that's a necessary condition, not sufficient, but imposing that non-double soft part of the amplitude vanishes already tells me, uniquely fixes for me the form of the phase shift. So it's not a proof yet that this integrable model indeed satisfies all the constraints, but it uniquely fixes for me the candidate integrable model. Yes. Okay. Yeah. Yes. Probably want to see this one. Right. Okay. Probably my writing probably is too large even for this set of blackboards. So yeah, this argument provides a candidate, the only possibility for this integrable this matrix to the IS LS squared over 4. So it's diagonal scattering with, so the only function which satisfies this condition is just the phase shift is linear in S. So as Misha correctly pointed out, this is a necessary condition. It's not clear at the moment that this is indeed the correct S matrix. So, well, actually, that will bring me somewhat far from confining strings, but I think it's instructive to spend maybe 10 minutes. So at d equal 26, we can, and it's only possible at d equal 26 and d equals 3, as I said. So in all other dimensions, we know that the integrable theory is impossible. Let's spend 10 minutes and discuss the equal 26 case, and let's derive this S matrix there in a more conventional way, because actually quite a few people were asking me how what we are doing here, how it corresponds to the standard way we talk about bosonic strings using Polakov description. So let me show to you how one derives this S matrix. So in the equal 26, the statement is that this is a S matrix which describes Wolf-Schmidt scattering for critical strings. So let me show to you how this S matrix comes about in the Polakov formalism. So in the Polyakov language, we describe system by Polyakov action, which is of course classically equivalent to Nambu-Goda. Squared minus h, where, well, so it's a kind of the simplest theory of gravity you can imagine. And there is a metric. So now we're interested in the long string and long string. So that means we look at the string fluctuations of this form. So it's convenient to work in the light cone coordinates. So here, y's are excitations around long string, and like x plus equals sigma plus and x minus equals sigma minus, that corresponds to long string background. And we're using parameterizations and while symmetry, we can fix the metric to be free. So work in the conformal or even flat space gauge. And now the y mu's, they satisfy free equations, right? So in these coordinates, y's are free. So in particular, we can write yi is there sum of e to the expanded over modes k sigma plus k tau alpha dagger plus complex conjugate. And sorry? No, because I can see the infinitely long string, right? So it is an integral, yes. Right. So I mean integral here. Okay. And in this language, y plus and y minus are not independent, but rather they're given by, they're fixed by Virasoro constraints, which can be, so the solution of these constraints can be written in this form. So I minus y minus, and there is, in principle, there is integration constant here, and similarly for y plus, there is analogous expression where basically one replaces pluses and minuses. Y plus or sigma plus. Well, actually, one can impose additional gauge constraints. One can choose these y's to be equal to 0, which corresponds to, so this is equivalent to imposing the version of the light cone gauge condition, which is suitable for this sector with infinitely long string. So this is equivalent to imposing condition that d minus y minus is equal to 0 and d plus y plus is equal to 0. So that's kind of a version of the light cone gauge suitable for this background. Now kind of one may be confused at this point. So we have a system of free bosons. So what S matrix I'm talking about? But the point is that the physical space-time coordinates, they're not this sigma and tau. They're like these y's. In particular, so when we talk about string which stretched in one direction, then really in asymptotic region, it means that kind of as our clocks and Rhodes variables, we're really using y0 and y1, or y plus and y minus. So I said this is kind of a very simple theory of gravity, and really kind of the only, to some extent, the only memory of the fact that this is a theory of gravity here manifested by the fact that what we call physical clocks and rods, they're themselves operators in this theory, this y plus and y minus. So what we need to do to extract then S matrix, how it looks in this using kind of this switch to physical coordinates, essentially what we want to do, we want to replace this in this expansion here, we want to replace sigma and tau with y1 and y0. Of course, it's somewhat challenging to make precise sense of these expressions. So, well, I have this solution to Virasoro constraint, but these are rather non-local operators, and I think it's rather challenging to make sense when I kind of essentially what I want to do. I want to rewrite this sigma and tau in terms of y's, but at intermediate times, it's somewhat challenging to interpret the expression, the results in expressions. But in asymptotic regions where I ask question about S matrix, actually everything simplifies quite a bit. Namely, if you look at this expression in this condition, under this condition that little small y's are equal to 0, if one looks at these expressions for y plus and y minus, then one finds that tau going to minus infinity, this y plus minus, they're just equal to 0. And on the other hand, at tau going to plus infinity, this y plus minus, they become just, if one recalls correct normalization. So these are just momenta, p plus and p minus momenta of my physical modes of yi's. So hence, by using these two relations, so I can now kind of, so as I said, what kind of I want to do, I want to rewrite the kind of Fourier expansion of yi's, but not in terms of sigma and tau, but in terms of these physical variables, which are sigma plus y and x sigma tau plus y. So, well, and by looking then at the two asymptotic regions, I find that from here, I conclude that what one calls in operators in asymptotic past, then let me call them A as opposed to alphas, which I'm using there, because these y's are 0 at tau minus infinity, then in the asymptotic past region, this A's A in are just equal to alpha. And in asymptotic future, instead, I find that they are different. They differ. Oh, I minus. They're equal by this expression. So e to minus I the squared p plus minus times p minus plus over 4. So what I did, I just rewrote. So I plug here, I wrote sigma as x1 minus y1 and tau as x0 minus y0. And from there, because of this relation, one finds this relation between physical creation operators in the for out state and these alpha creation operators. Well, and now when one has this expression, then one can just go ahead and calculate the S matrix following its definition, namely by expressing, so the in state is given, say, let's look at the two particle in state. So we have I plus of plus a j of p minus is equal to 0, acting on the vacuum. So this is the same as acting by these alpha operators on the vacuum, and then by using, and then we write it through a out operator. So this becomes e to the I l squared plus minus over 4 a out vacuum times the same e to the I l squared p minus plus over 4 times a in p minus in the vacuum. And so from here one reads, so actually it's important here. So if one being slightly non-accurate here, one may forget that these are operators. So basically it's important, out of these two operators here, only one leads to some non-trivial effect, because this operator acts on a state which doesn't have yet any particles, any p plus particles in it. So actually this exponent gives 1, but this exponent now acts on the state with non-trivial p minus. So this exponent produces non-trivial phase. So what's written in this line, then it becomes just e l squared s over 4 a out plus of p plus a out plus of p minus. And this relation between out state and in state, just by definition of S matrix, tells us that this is the correct S matrix which one gets in the Polakov formalism. So that proves that in D equal to 96, that S matrix which we fixed by previous argument is indeed the correct S matrix. Well, there are several comments to be made on it. Well, first of all, and that's, yeah, let me think which one. Well, let me mention briefly, I won't really need it, but I think, well, it's interesting that in general number of dimensions, one can extend this argument and obtain simple generating function of all these anomalous one loop amplitudes which lead to particle production. Namely, in general number of dimensions, one cannot use the Polakov action because of the Weil anomaly. So that's not the right action to use, but one may use so-called Polchinski-Strominger formalism, which amounts to modifying this action. So adding to Polakov, consider the action which is a sum of Polakov action plus Polchinski-Strominger, where this PS term has the following form. It's d minus 26 over 24 pi integral d to sigma square root of minus h alpha beta. So it looks as a linear dilaton theory, but here this phi is not an independent field, but itself a composite operator of my theory, so of this form, so minus 1/2 log of dx squared. So, which it shows, and this action is chosen in such a way that phi transforms under Weyl transformations and transforms like by shift, and this action just like really elementary, like fundamental dilaton. This action spits out a piece which cancels anomaly coming from integration measure. So this full action, which is the sum of these two terms, is Weyl invariant now. So this action looks scary because, well, it's very non-local. So when you have this log of dx squared, and when you act with it on the derivatives, then you get dx squared going in the denominator. But remember, we're using this to describe scattering around long string background. So when you expand this action around long string background, then as an effective field theory, it makes perfect sense. And then by essentially going through all the same logic, so one solves Virasoro constraints and plugs the result back. So then, in addition to this phase shift, which comes out from the redefining asymptotic variables, so when you plug in this phi, when you solve exclude y plus and y minus in terms of other y's in this action, then this term, it becomes just generating functional for one loop amplitudes which lead to particle production. So one can clearly see the kind of connection to the usual way to discuss anomaly. So in particular, it makes it manifest that all these anomalous amplitudes, they are all polynomial. So they all look local from two-dimensional perspective, and they come out from expanding this piece in the action. Okay, so I'm slowly going back to confining strings, but for the future, let me make a few more comments. So that first of all, that argument, it was about d equal 26 case. So far it says nothing about d equals 3, because well, in d equals 3 situation is somewhat subtle. So in d equals 3, in principle, one may try to use this formalism, and one does get e to the ISS matrix, of course, and this term at leading node, it vanishes on shell, but still this is not a UV complete series. So one cannot, so somehow this term definitely doesn't vanish on shell if one looks kind of before imposing Virasoro constraint. It's kind of changes the central charge of the theory. So usually when something vanishes on shell, we think we can remove it by field redefinition. So at d equals 3, we cannot remove this term by field redefinition. It doesn't contribute to on-shell scattering amplitudes for a long string, but still we don't have a formulation of a theory. So this argument cannot be used to argue that S matrix e to the S really describes nonlinear as integrable model with nonlinear Poincare symmetry. So let me make a few comments about that, which will be somewhat important later. So first of all, well, this S matrix which we obtained, this e to the SS matrix. So e to the S is really a sum of Feynman diagrams, right? By that I mean the following. So exponent, the series for exponent is it's an absolutely convergent series, and so that means kind of there are no non-perturbative effects in this S matrix. So really, order by order in Lorentzian expansion, every term here is coming from Feynman diagrams. So even though it's, yeah, by the way, some little kind of miracle happened here. We started with an analysis which was just going on at Lorentz effective field theory. But at the end of the day, imposing this extra constraint of integrability, we managed to find a quantization, at least in d equal 26, which works at arbitrary high energies on the bullshit. Well, and d equals 3, it also provides a candidate S matrix. So, well, as I said, it's a, yes. Well, what happens at d equals 3? So kind of looking at this form, it looks like there is nothing special there. But after you solve the constraints and try to write down what would be the corresponding amplitudes, they all vanish on shell. It's clear to see, because what happens, the terms which one gets from this term when one goes kind of removes x plus and x minus, they all have the following form, just in terms of derivatives. There is the d plus squared x, d minus squared x, and just by counting the derivatives. And then there is d plus x to the n, d minus x to the n. So by expanding this term, one gets only terms of this kind. So if these x's carry some flavor indices, as it happens at d larger than 3, then this may be non-trivial on shell. But if there is a single flavor, like it happens in 3 dimensions, then what's written here is the same as d plus of d plus x to the n plus 1, d minus of d minus x to n plus 1. And now I can integrate by part, and it vanishes on shell. So this term vanishes on shell when one tries to calculate the scattering around long strings. But in the full theory, it's definitely non-trivial. It cannot be removed by field redefinition. So that's, if this theory like that exists, that's not the right language to describe it. So we have a proof that at d equals 3, this theory actually exists, in the sense that it's this model also at d equals 3 has non-linearized Poincare symmetry. Yeah, I won't be able to reproduce it on the blackboard, but let me give you an idea. So it's based exactly on this. The idea is based on the fact that this S matrix is really just some of Feynman diagrams coming from some local action. And the proof goes inductively. So basically we assume that so we're trying to imagine, so we start with Nambu-Goto action, and imagine we start calculating amplitudes, and we allow ourselves now to write counter terms in high order derivative expansion, and we're asking ourselves whether we can reproduce by adding more and more operators with more and more derivatives, whether we'll be able to introduce this, reproduce this S matrix. So at leading order, Nambu-Goto action does the job. Also at one loop order, as we discussed last time, there is no counter term to add. So if the procedure fails at one loop, as it failed in d equal 4 and higher, not equal 26, there is nothing we can do. But the moment one goes through d equal through one loop order, then inductively, so we're kind of assuming, okay, maybe by doing this calculation, and at some point you get a term which violates integrability, which leads to particle production. And first of all, this term should be local from two-dimensional perspective, because, well, actually, that's kind of another ingredient. So the theory with this S matrix satisfies all what you want from two-dimensional theory to satisfy. So it defines some well-to-do two-dimensional theory. And actually, well, there is a name for this theory. This is these days it's called a TT-bar deformation of d-2 free bosons. So, and the fact that it satisfies all the conditions, it tells us that one should be able to write a local Lagrangian, which will produce this S matrix. So that means that when you start doing these calculations, and at first time you get term which leads to particle production, one can write a two-dimensional counter term which would cancel this particle production. Otherwise, well, TT-bar, that theory wouldn't exist as two-dimensional theory. And then one proves that at beyond one loop order, one can always covariantize this counter term. There is always, this counter term can always be written in the form which is compatible with Poincare symmetry. So that's the gist of the argument. So well, we have it in the paper. We can discuss more if you're interested. Well, it's, but here, well, the argument goes order by order in derivative expansion. So order by order derivative expansion, this is matrix that satisfies all the properties which it needs to satisfy. It can be, so which means more or less by these properties which we like about this matrix, they're really kind of by designed to ensure that in the regime when we can expand, perturbatively expand, that this matrix should be possible to reproduce from local Lagrangian. And the point is that this S matrix, it has the form such that it it's low energy expansion just gives a absolutely convergent series for it. So there are kind of subtleties, and kind of what you're referring to refers to the fact, refers to this behavior that this S matrix doesn't look like S matrix of quantum field theory. So in particular, this behavior at infinity, which one has here, it's incompatible with the existence of the UV fixed point. But this argument, which we kind of it's purely diagrammatic, so we still it doesn't prevent this argument. So most likely this theory doesn't have local shell observables, for instance, and has many other interesting features, which are not so surprising if you think how we got it. For instance, D = 26, we got it by quantizing theory of gravity and introducing this relation observables. But that doesn't affect this argument. Well, with the caveat that we could have made a mistake, it's really rather messy and argument. But the statement is that at D = 3, in principle, there is this integrable S matrix, which also has a nonlinear realized Poincare symmetry. Well, I don't have a guess. And well, actually, I suspect that there is no consistent theory like that, but I don't have a proof of that. Well, and my suspicion comes from the following: this kinematical constellation, which happens here, it's similar to another kinematical constellation which happens in D = 3. Namely, if we quantize string theory in the light cone gauge, right there, and D larger than 3. One finds, so there is this anomalous commutator, right? G plus I, G plus J, which is not equal to 0. And that's unless theory lives in 26 dimensions. And that's why we want theory to live in 26 dimensions. But of course, this commutator vanishes at D = 3. So one may actually say, oh, it looks like light cone gauge defines a well-to-do string theory also at D = 3. And actually, for instance, Townsend and Mizinchesko tried to make this statement. And then went ahead and then, so now I'm talking about really kind of short strings, and went ahead and tried to study this theory. And what they found is that, for instance, they calculated helicities of the states which one gets in this theory. And what they found that necessarily, if one looks at the helicity of the state, that the theory will contain anyons with irrational spins. Well, actually, they found it interesting. So they say, well, maybe it's a candidate theory for anyons. To me, it looks very suspicious because kind of we started with a theory which is one variant under Poincare, and then ended up getting irrational spins. So it looks like a sign of anomaly. So to me, it's really looks reminiscent of situation with the chiral anomaly when and then C larger than 2, there is an anomaly in local commutator, and then C equal to 2, there is Witten's anomaly, global one, which you don't see in local algebra. So to me, it looks a little bit like that. So I strongly suspect that this theory kind of as a theory of really full-fledged string theory, which would describe also closed strings, is sick. And in particular, we have some evidence for that also. So in D = 3, for long strings, I already said that I showed this data. For long strings, we know Young-Mills doesn't describe as this S matrix. But also, if one looks at the global spectra, so one may ask the following. Let's just do some counting of states of the globals. And I won't have time to describe that, but in D = 3, actually, well, for instance, there are clearly states which can be associated with string levels. And one can just say, okay, let's ignore the information about spin, and let's just try to compare the actual global spectra, which one finds in the Young-Mills. Let's compare it to this D equals 3 model in terms of counting multiplicities of states. And one finds more states at the in globals that they're in this light theory. And actually now with well, with Shahrzad Zari, who's here, Gabriel Coma, and Guzman Hernandez Chifte, we close to understanding where these extra states are coming from. They roughly correspond to some difference in counting topology of the phase space from the usual light cone quantization. So the short answer is I don't have a proof, but I strongly suspect that theory doesn't make real sense as a full-fledged string theory. But as a theory for long string, somehow it provides integrable model which has not linearly realized Poincare symmetry. And I spent so much time on that because it will be important in later on. Okay, so how I'm doing on time, by the way? When did we start? Start a bit later, right? So, okay, good. So yeah, probably, yeah. Let's, as promised, I'm planning to show you some data. Maybe not today, but let's get back. So let's come back to QCD strings. So that was kind of end of theory part, and let's get to experiments. And as I said last time, what experiments or lattice simulations, what they provide for us, they provide finite volume spectrum. And I'll show the data maybe this time or next time. But let me, before showing it, let me preview some of its feature. And well, in principle, kind of how to interpret this data and how to extract information from it. So in principle, one can follow two directions, and both are instructive. So first of all, one may try using weakly coupled AFT description, which we have at low energies. One may try to calculate finite volume spectra and compare it with the finite volume spectra, which one finds. And one expects that at least for some subset of states, for sufficiently large compactification radius and for low line states, because theory is weakly coupled, one expects to find a good agreement. Of course, there is another direction which perhaps more interesting, namely, and that's also what people kind of try to do on the lattice for in high dimensions and for pion scattering. So in principle, one may try to, without relying on perturbation theory, but going from finite volume spectra, say something about dynamics on the Volchit theory. So really use it as a kind of experimental tool. But of course, two often relies on one. So especially because for instance, there was an assumption here, our weakly coupled AFT had only massless particles. So in particular, there can be massive particles on the Volchit. And well, as you already heard from Java, actually there will be one in 4 dimensions. And if it's sufficiently light, if such a particle appears at sufficiently low energies, then it can be in the regime when one still have some control from effective field theory. And that's where you need then to have reliable FET calculation to say that, to deduce from the data that such a particle exists indeed there. Okay, so let me say a few words about how one is being done. Which one?
The relation to the S matrix of the finite volume spectrum.
Well, actually, that was first we got it that way, right? And indeed, by looking at the finite volume spectrum, so there is basically by opening Palczynski's book and looking at the spectrum in the sector with winding 1, well, there is a spectrum which I'll write soon, actually. The leading order binding energy in the large radius limit, it is determined by the phase shift. Yeah, that's in some sense the simplest way to get S matrix, at least. Right. So here I went a little bit more in the perverse way because I wanted to illustrate that one can push this logic of Goldstone bosons really that far without relying on string theories. So to reconstruct critical string theory. So I find it amusing, but you're absolutely right. That's maybe a more economical way to get that S matrix. And of course, that provides additional cross-check that that S matrix is correct, indeed. So yeah, let me say now a few words about this one. So there are two approaches which one may follow. One is kind of what people traditionally were using in these studies, which I would call naive perturbation theory. Namely, what one does, one has a theory in a circle of size r. One does KK decomposition. So we have an action, we have our effective field theory, which is a leading order just given by Nambu-Goto action. One does KK decomposition, one gets a bunch of, well, there's a leading order, one has a bunch of KK modes with momenta 2 pi n over r. And so one has a kind of, one decompose, one gets a kind of large quantum mechanics of infinite set of these KK modes. There is a dimensionful interaction coupling constant with the LS. And so one just expand, one calculates finite volume energies perturbatively by expanding in LS over R. And one observation which was made early on, but well, it goes back to Lusher in 1981, but Lusher didn't use the full power of non-linearized Poincare symmetry, and then later it was emphasized by the works of Haroni, that there is large degree of universality in this expansion, simply because it should be clear from what we were doing so far. We already said that in the first non-universal operator, which appears on the wall sheet, it's the form k to the 4, where k is extrinsic curvature times ls to the 6. So if one thinks then about energy of a generic state in this ls over R expansion, then there is a piece which is just classical tension of a string. Then there is some 1 over R piece, which may be coming from kinetic energies of Goldstone bosons. So for vacuum, it's the Casimir energy. That's what's called Lusher term. Then there is C-1, C-3, ls squared over R cubed term plus C-5, ls to the 4, R to the 5. So the expansion goes in the even powers of ls squared. And finally, there is a term C-7, ls to the 6, R to the 7. And this is the first term which is non-universal, which is sensitive to these higher order corrections in the action. So all these coefficients which appear here, all terms up to the order of R to the 5, they're all universal and fixed by symmetries. So this is kind of the story on the series side. And then what happens? So then one goes and compares the result with lattice data. And then something interesting happens. Namely, one finds that the vacuum energy of a string is indeed very well reproduced by this perturbative expansion. And actually, it's only now that the lattice precision reaches the limit where one can start being, it was supposed to be R to the 7. 7 should be upstairs. But anyway, when one starts being sensitive to this non-universal corrections. So for the ground state, it works very well. However, it works way worse for excited states. Actually, it's really for the range of the strings which are for the R, which are observed on the lattice, it doesn't work at all. Essentially, I'll show you the plots, but it works very poorly for excited states. And instead, what was observed is that the following formula. This to the 4 plus that for most states, one gets very good agreement up to quite short strings by using this formula. And so what this formula is, it's essentially, that's what Ed was referring to. Well, this is their, if I plug here the d equal 26, that will be the formula for string excitation energies of string states in the sector with winding 1 for critical string. But of course, we're not in d equal 26, so the formula was used with d equal 4 on d equal 3. So this formula is what you obtained, again, by doing quantization of bosonic string in sector with winding number 1 using light cone gauge in general dimensions and basically closing your eyes on the fact that that's not the correct theory. So it was a strange situation when kind of the answer which is wrong was reproducing the bulk of the data much better than kind of correct procedure, correct perturbative expansion. And clearly this is a sign that something kind of probably has to reorganize this perturbative expansion. There should be some better way of doing perturbation theory. Yes, John. Right. Yeah. And that's yeah. So we can actually that's kind of to get the idea of what's going on. It's just instructive to look at this formula and to see kind of what happens if we try to expand this formula. Well, this formula there is a square root here, so it has a finite radius of convergence. And for ground states like this n and until there's levels of the kk modes, total kk momentum moving left and right. So they're all equal. They are all equal to 0, and so the radius of convergence is kind of we expand in 1 over r, and so it's fixed by this vacuum energy. It's pretty large radius of convergence in 1 over r. And until that, this is a total left moving and right moving kk momentum. No, it's a usual, but it's a bosonic string. Well, maybe what is maybe somewhat unconventional here. So this term, usually when we look at the spectra, this term wouldn't be there because for strings without winding, n should be equal to n tilde. But here I'm talking about the excitation in the sector with winding number, so there is no level matching condition. So n and tilde, they're just two independent numbers, right? Yes.
So this comes from polyconversion or polyconversion?
No, this comes just, well, we call it it's basically polycofaction quantized without the Polchinski parameter term. So yeah, so it doesn't even correctly, actually, that's a very good point. So this spectrum doesn't even correctly reproduce all universal terms, but because universal terms, they include these one loop effects, which are lead to, so there are states. So here the states with the same n and tilde are exactly degenerate. And this violation of integrability related to the term, it leads to splittings between the states. So this spectrum doesn't even account for that. It doesn't have all the universal terms, but still it reproduces quite well, actually. You see, at first sight, remarkably well, most of the states. That was kind of the puzzle. Yes. Right, the tachyon. So we're here with we're studying the sector with winding, right? So as I said, I want to work with a sufficiently large value of R, where center symmetry is unbroken, and that's a sufficiently large value of R. There is no tachyon. So in this language, the presence of this tachyon, well, it's small r, the winding state, there is a winding tachyon, the low state becomes tachyonic, but actually it's a welcome feature for, if you think about confining theory, that corresponds to center symmetry breaking for small radius. But at large R, there is no tachyon in this sector. Yeah, so, but coming back to what I was saying, so one kind of sees what's going on here, that even kind of, that's the exact answer for the spectrum. We can try to expand it in powers of 1 over R, and we see that this expansion will work much better for ground state than for excited states, simply because for excited states, there is this additional, the radius of convergence is kind of suppressed by these factors of n and tilde. Because these are kind of large numbers here. Well, and one might phrase it in more physical terms. So kind of what are these factors? What are they associated with? So it's kind of from this, looking from this formula, it's clear that it's useful to think about finite energy spectrum as a kind of function of two different variables. So you have some general excited state of a string, and there are some excitations which will propagate on the string. And these excitations, they have some momenta p, and there is dependence. So the energy of excited state depends on this momenta, but also it depends on the compactification radius. And what kind of naive perturbation theory does, it plugs for this momenta, it plugs here p is equal to 2 pi n over r, plugs it here, and expands this whole function directly in the powers of Ls over r. And instead, it's and what one wants to do, one wants to find a two-step procedure where one disentangles these two expansions. And so, and that's, well, let me write it in the center because it will be important. So okay, yeah, I'll outline this logic, and then next time we'll see the results. So, and that's where, as I promised you, thinking about Walsh-T test matrix will prove to be useful not just for theoretical purposes, but for these practical applications. Namely, the idea is to reorganize the expansion in two steps. So two-step procedure. So one step, one works as infinite volume, and in infinite volume, that's where one uses perturbation theory. One applies infinite volume AFT and calculates perturbatively S matrix for scattering of the string excitations. Well, and the second step, so can we all believe that if you know S matrix exactly, the principle that it has exact information of like full information about the theory. So in principle, it should be possible, independently of the fact that we calculated S matrix perturbatively, it should be possible to go exactly between S matrix and a finite volume spectrum. So that's the idea of what we want to do. Instead of directly calculating finite volume spectrum and perturbation theory, we want to calculate perturbatively the S matrix and then go exactly to the finite volume spectrum. Well, unfortunately, this step, even though kind of we believe that there is an equation which determines the finite volume spectrum in terms of S matrix, it's not known how to do it in general. However, there are several special cases where it's known, and it's a classic problem in lattice field theory, because I already said before, that's one of the things which lattice one can do on the lattice. On the lattice, one measures finite volume spectrum, and one wants to extract from their scattering amplitudes. So there are some cases where it's known how to proceed. So first of all, it's a massive theory below multi-particle threshold. Multi-particle threshold, or the theory or integrable 2D model where there is no multi-particle production. Then there are so-called Lusher formulas, or in the integrable literature, also known as asymptotic beta ansatz. So this is a set of equations which allows to find finite volume spectrum up to so-called winding corrections. So these are exponentially, in this case, these are exponentially small terms which behave like that. They're associated with virtual particles traveling around the circle. And schematically, these equations look like that. So you have particle I. So you write quantization condition for its momenta, delta of pi pj, where these are other particles present on the circle. You write this quantization condition, and then calculate energy as square root of pi squared plus m squared. So and actually, well, there are further things, but that's the main improvement. So there are other improvements which are important, but that's the most important one actually. So naive perturbation theory would correspond to which I described before, would correspond to expanding this equation perturbatively in delta. Right, and plug in p is equal to pi NOR, and that would reproduce what I was calling naive perturbation theory. And roughly speaking, what this does, it kind of you might say it resounds kind of classical non-linearities associated with particles going many times around the circle and scattering many times. In particular, when phase shift is a rapidly growing function, then the momenta which one gets from solving these equations, and it can be quite a bit softer than the free values. And low energy expansion works at small momenta, and the kind of real condition for low energy expansion to be good is when physical momenta are small, but not 2 pi NOR over small. So this procedure, so doing it this way, and that's what lattice people always do in high dimensions, of course, that improves the convergence quite a bit. So I'm nearly ran out of time, but let me say, well, to kind of that's the main idea. Unfortunately, well, what is said here is not enough for us. First, our theory is not massive. It's massless. So that means these winding corrections they're power law rather than the exponential. So we need to account for that. So in integrable models in 2D, there is a generalization of these equations, which is known under name of thermodynamic beta ansatz, and that allows to calculate calculate finite volume spectrum, also including the winding corrections. Now, of course, at the end of the day, our theory is not integrable, but the logic is that we calculate to certain order in LS expansion, and up to the order at which there is no particle production, we apply this technology and go to the finite volume spectrum exactly. And there is yet a while, probably next time I say there is another way to think about it, but that's the main idea. That's kind of how one improves this perturbation theory. And in particular, if one proceeds this way, that not surprisingly, so at the very step at 3 level, so there is square root formula. Yeah, I think I erased it, but it's related to adds comment, and also it's kind of cross-check of that S metric. Yeah, I erased this square root formula, but in this procedure, at the very first step, one calculates 3-level amplitudes and gets this linear phase shift, and then if one plugs that phase shift in TBA, that reproduces back this square root formula, which was matching the lattice data better than the naive perturbation series. So in this way of organizing perturbative expansion, the square root formula really comes out as a leading order answer. So one is not surprised that it actually describes many of the states quite well. So yeah, let me pause here. I'll tomorrow say a couple more words about this procedure, but that was the main idea. And then I'll show you the results.
So it was not clear to me, how do you know that the corrections, the ones that you cannot describe with integrability, are smaller than the things you're resumming inside?
No, the logic is that I always I believe that there is exact equation which relates S matrix and finite volume spectrum. Even if I don't know this equation, but I believe that such equation exists. So I'm doing perturbation only at this stage, right? And I'm calculating S matrix perturbatively, but now sometimes I have, like if this S matrix turns out to be sufficiently simple, for instance, if it's not, well, if it's given order in perturbation theory, it looks like there is no 2 to n processes. Then I know exact relation between S matrices of that kind and finite volume spectrum. And I'm using this exact equation. Well, exactly. I'm not expanding at this stage. So that's the logic. If
the 2 to 2 S matrix satisfies Young vector at that order is still integrable, then you trust TVA to be doing the exact job.
Right.
Yeah,
right. That's the idea of what we're doing. Well, and that's kind of also usually, that's what also usually done in lattice gauge theory. Well, I think it's more, it's a statement that, well, kind of, you can study classical nonlinearities exactly, even if you're doing kind of perturbative expansion in the quantum model, right? So there are some effects which you don't need to expand everywhere, right? So if there is exact part of the formula, then it's okay to use it, roughly speaking. But maybe next time, at least in this particular case, there is a kind of trick which I think makes it conceptually even simpler. But well, I mean, it's well. If I have 1 more minute, I can. Okay, good. Then I'll tell you later. But that trick, I think it's based on TT bar deformation, formulated in terms of TT bar deformation. But really, morally, I think what I said is the correct logic also, which is always used. Yes. Right.
Okay.